Okay, we study Y5 electrostatic potential. We learned how to compute the electric field due to a distribution of charges based on the theory of Coulomb force. Today we study electrostatic potential, and just like the gravitational potential we learned in last semester, we consider the integration of the electric field and put the negative charge on it. And we need to allocate a certain value at a reference point, and that does not contribute to any physics at all. So if you take the derivative of this electrostatic potential, and because of this negative sign, we again put the negative sign on it, then we will obtain the electric field. That electric field, because of the integration, is removed by taking the derivative. We can obtain the electric field by applying minus gradient. For convenience, in most cases, when we consider electrostatic potential, we usually choose a 0 as r goes to infinity. However, it is our choice. So we can always change the absolute value of potential. That does not make any difference in physics. That concerns the electric field only. We learned Stokes' theorem, and we will review this later before we concentrate on Maxwell's equations. The core of the electric field, because the electric field is central, the core is always a 0. When core is a 0, it is automatically electrostatic force becomes conservative. The reason is that the core evaluated over a surface is identical to the path integral over a closed path that is the boundary of surface. So surface integral of this curve becomes the line integral along a closed path. When curve is a 0, this integrand is a 0. That means this closed, if you attach a charge Q, then it becomes a force, and force, scalar product, displacement is the work. If you come to the same place, and the net work done by the electrostatic force is, because the left-hand side is 0, it is always 0. Work along a closed path is always 0, that means conservative. Every point, the kinetic energy is completely fixed as a constant value. That is the very, very important point of conservativeness of this electrostatic force. Unfortunately or fortunately, this curve is not 0 anymore when the magnetic field depends on time. This is the main source of generating electric field, and our electricity is generated by generators that is governed by this Faraday's law. Due to this, the magnetic field change in magnetic field generate the electric field. However, when the magnetic field is independent of time, then the right-hand side becomes 0, and curl E is a 0. When curl E is a 0, due to this region, electrostatic, static. it doesn't independent of time. Independent. When the electromagnetic field is independent of time, then the electrostatic force is completely conservative. Although it is not conservative anymore, in the sense of the electric field, this relation gives us a deeper understanding of the conservation of energy, because the energy source is not isolated to the electric field. Instead, electric field and magnetic field, they communicate each other, and the total sum is conserved. This is a tremendous discovery by Maxwell. Potential and potential energy. Potential energy is just a potential energy. However, it depends on each particle's charge. If we use potential instead of potential energy, it is more convenient because we can replace the charge, then we can still make use of the potential. Just like the case Coulomb force, once you know the electric field, we just multiply charge cube. When you want to compute the gravitational force, you just multiply mass to the constant gravitational acceleration. Just like that. This is carbon copy of the parallel concept. In mathematics point of view, the two theories are identical to each other, but physics is absolutely different. Anyway, the change in potential energy is just a change in potential multiplied by the charge. You know, if as far as we consider magnetic field change doesn't happen, in that case, electrostatic force is conservative. When the field is conservative, then we can always make use of the total mechanical energy conservation. This is that. This is what? Delta U, that is the potential energy. If you move this one to the left-hand side, the change in the total change in T plus U, potential energy and kinetic energy sum, is always invariant. Invariant means independent of time. It is always constant. Units. Charge, Coulomb. Potential, volt. Work, energy, joule. And joule is a unit of energy. Energy is a force multiplied by the displacement. These are SI units, all relevant SI units. As you know, the fundamental electric charge, that is the elementary charge, that is the absolute value of the electric charge of the electron, or the electric charge of a proton. That is exactly defined like that. We don't measure further anymore because every electron's charge is the same. So instead, we have redefined usual definition of Coulomb or any other things. So do not be confused. E, if I write E, then E is a positive number. So electron's charge is minus E instead of plus E. Plus E is for the proton. So remember, as far as I'm teaching, I'm always using positive value for E. So electron's charge is minus E instead of E. Equipotential surface, equi. the same. Contour, there's a mountain. The line connecting the same points of same altitude, we usually call contour. If you look at the map, there are contours. These curves represent the points connecting the places with the same altitude. Okay? If you replace the height or altitude with electrostatic potential, then there should be points connecting them all together, the same potential. So that is an equipotential. And actually, the potential, electric field, they are all function of position. So these fields are function of the three variables, x, y, z. And additionally, later, when we consider electromagnetic transmission through electromagnetic wave, then we have to consider the time-dependent field. But right now, we are considering electrostatic case that is independent of time. Then we have only three variables, x, y, z. So this function has the constant value. Then it is not a line. It is a line in a two-dimensional distribution. This is two dimension, and the height is different one. The same height makes a contour that is one-dimensional object, but the distribution of electrostatic potential, if you connect the points with the same potential, it becomes a surface because we have a three-dimensional space. A simple example. We consider the equipotential surface due to a point charge. There is a point charge at the center of a sphere. Electric field is always a radial. Okay. And the distance from the center is defined like that. That is the radius from the center. And the direction unit vector along the electric field is always along the radial direction. Here, theta is the angle measured from the z-axis. That is called polar angle. And phi, if we choose x and y axis like that, then we have a planar radius rho, and we can measure the angle from the x-axis, and that is called azimuthal angle phi. Then unit radial vector is always expressed like that. What is the electric field? Electric field can always be toward this unit vector. And how can I compute the electric field from the potential? Just minus derivative. The main variable is r in here. So along this direction. So we take the derivative with respect to radius r. But we remember the electric field integration and put the negative sign on it to find the potential. Because of this, we take the derivative and then put the negative sign to cancel this negative sign. So that's the reason why we always have to put the negative sign. In general, whether it is this kind of a spherical symmetric distribution or not, removing this integral is to put the gradient. And you remember in the Cartesian coordinates, gradient is this, Y derivative, Z derivative. In general, some of these. However, in this case, there is no theta, no phi dependence in the electrostatic potential. Therefore, what we need to do is just along a single direction, that is unit radial vector, and the derivative is with respect to r only. What happens to the case if the distribution of charge is along a straight wire? Electric field has a symmetry. You know, for example, we do not have this direction that contains a z-axis, because if you cut it off into two equal pieces, because of the symmetry, the electric field generated by the lower wire is more or less this direction. Due to the upper wire is along this direction, they are symmetric. Hence, the z-axis contribution is exactly cancelled. Only the planar radial direction survives. So even though we are in a three-dimensional space, this infinite wire will remove a single dimension, and we are left with only two-dimensional distribution. So electric field, for convenience, let me remove the z-axis, and our world is shrunken into two-dimensional space, and the electric field is always along the planar radial direction. That is completely determined by this. And you know, for example, this is a row vector, and row vector can always expressed in terms of unit vectors of x and y axis. Introducing the azimuthal angle phi, then it becomes a linear combination of cosine and sine to the x and y axis. Again, the electric field is a planar radial direction, so the minus gradient to obtain the electric field from the potential is simply a single derivative along the planar radial direction, and put the negative sign on it, and the unit vector is along that direction only. You know, even though there is a E row, the radial direction, there is also tangential direction, but that contribution does not exist in the electrostatic case. Next, we consider uniformly charged infinite plate. This is a simplistic case because of the symmetry. If you are placed at the center of the uniformly charged disk, then electric field is perpendicular to that disk. Okay? If it is a positively charged plate, the electric field radiates. If it is a negative, then electric field enter into the disk. Again, we compute minus gradient of the potential, and minus gradient in this case is only electric field is only along the this direction, so our derivative is a single derivative along the z-axis only. Parallel plates, because of Gauss law, or you have evaluated electric field due to a disk, and the checkpoint will give you a detailed computation of the electric field, and the final result is that sigma is the charge density per area. You know, the electric field is trapped inside the two charged plate of equal charge density. And in here, electric, because sigma is a positive, electric field is like that. So from here to there, potential must increase. Positively charged is a higher potential. Negative charge potential must increase. And outside the electric field is zero. So there is no change outside in the potential. Okay, And then why don't you take the derivative? This is a positive. However, we need to put minus sign to find the electric field from potential. Potential increases, its derivative is a flat, positive. However, we need to put the negative sign on it. So that's the reason why the electric field is opposite direction. So in here is constant, outside 0 is a linearly increasing, and electric field in opposite direction of increasing potential. Electric potential difference will result in the change in energy. Electrostatic potential of monopole can be computed directly from the definition. We have chosen the reference value to be 0 when the reference point becomes infinite. You know this kind of integral very well, and move this negative sign, and we know that this is a derivative of 1 over r. So from 0 the infinity to a finite radius, you will find the electric potential due to a point charge that is a monopole, 1 over 4 pi epsilon 0 q over r, where r is the distance from the source charge. If there are many charged particles, then we can just add them up algebraically. This is due to the superposition principle. What happens to the case of dipole? Dipole consists of two oppositely charged objects whose magnitudes are the same. Therefore, this guy has an electric field in this way. This guy has an electric field in opposite way. You know, Coulomb force is depending on over 1 over r squared, and the potential is 1 over r style. When there are two oppositely charges of equal magnitude, this contribution cancels exactly. Because of the exact cancellation of 1 over r dependence in the electrostatic potential due to dipole, this results in 1 over r cubed electric field, and this results in 1 over r squared potential. Okay, that does not happen in the gravitational case because masses are the same, all the same, positive only. Okay, r plus and r minus is the distance from the positively charged particle to a field point. Let me see, the field point, negatively charged. However, the cancellation is not really exact. If you go very far away, these two are almost similar, but if you come closer to the center, this approximation is not good anymore. Anyway, if you assume r is much greater than this distance d, and we define electric dipole moment to be qd, and the unit vector n hat that is along the direction from the negative to positively charged particle. You know the binomial expansion very well, and if you apply this one to this and substitute a equals a minus 1/2, then binomial expansion looks like that. Therefore, distance from the charged particles from plus minus becomes like that. If you ignore the higher order pieces, then it's simply we have different sign in the next order. So the leading order 1 over r, and that next leading order is a d over r cosine theta. cosine theta is the angle between this direction and the direction toward the field point. Because of this, if you subtract 1 over r plus minus 1 over r minus, then this term vanishes exactly, and only this guy survives. That's the reason why we have electrostatic potential due to dipole is of higher order than the monopole. The electric field is much weaker and attenuates very fast in comparison with the monopole. If you extend this idea, we can introduce electric quadrupole. There are 4 charges. Even I can cancel this 1 over r square potential and refine the expansion more accurately. However, in our class, we are only interested in the electric dipole, and the approximate value for the electrostatic potential due to a dipole is like that. If you have an electric charge distribution, continuous one, we have to integrate the charge over space. Depending on the dimension, sometimes it is a line or curve, surface or volume. You have to do this integral to find out the net electrostatic potential at a field point. Once you find out the electrostatic potential, you apply gradient and put the negative sign on it, minus gradient, to find the electric field. And many of the checkpoint problems give you a very nice examples trained by yourself. When you need to do some calculation, you had better to find out the best coordinate system. For example, if you consider a line charge distribution along a straight line, in that case, you had better to choose this kind of coordinate system called the cylindrical coordinate system. And in that case, their electric field can be computed in such a manner. This problem is exactly solved in the checkpoint Y5, and you can repeat that calculation. Let me tell you the final result. This one, if you take the derivative, you find the electric field along the z-axis, and if you have what's that, r increased r to infinity, in that case this guy disappears and only sign of z appears. That is the one we obtained. Sign is opposite in 2 directions, depending on the electric field is radiating from the plate normal direction. But in general, it does have some different value. But if you assume that you are placed very near to the plate, that is in effect r goes to infinity region. In that case, this approximation that the electric field is right and left sigma over 2 epsilon 0, that is almost exact. System of particles, you need to compute the all combinations of, for example, if you have 3 particles, potential energy can be computed by combining all possible pairs, and some of them will construct the potential energy of the total system. We know the isolated charged conductor. This is a different one than the gravitational force. Electrostatic potential related to charged conductor, because conductor allows any net charge allows them to flow inside. So electrostatic equilibrium is to be reached to make the electric field inside the conductor always vanishing. So inside the conductor, if it is in equilibrium, you have to assume the electric field inside the conductor is vanishing. If E equals 0, then directly you will find the potential is constant. That's the point.